As I built this app, I took the code I used within it and created a CN1 lib that implements the native interface described here. So a better way to implement Braintree support would be to use the official Braintree CN1 lib. However, this is still useful as an educational tool explaining both Braintree and how to map a native interface. Braintree is a pretty simple API on the client side, as most of the charging process is handled on the server side of the API. The reason for this is that the client side is far more hackable, even in a native app. In order to work with the API, we start with a token, which we can get from the server code, and then perform the charge process, which is handled mostly seamlessly by the library API. If you go to the Braintree online docs and look at the integration instructions for native Android code, you will find this code. This is native Android code for making a request. The token is something we need to get from the server, although conveniently the Braintree site provides a helpful debugging token we can work with. This can fit right into our native interface. But first I want to review the native API to decide what sort of native calls we would need. Notice that even though a view object is passed, it isn't really used, and that a token value is needed even though it isn't passed. Moving to the iOS side, the Objective-C code isn't as readable for Java developers, so let's review this in pieces. This is a method declaration that accepts one string argument. Technically, in Objective-C, these are messages, not methods, but I won't go into subtle language differences. Here we allocate a request. Notice that this is the equivalent of a new call in Java. The init entry is a method invocation of init. Methods are invoked using a square bracket syntax. Init is a special case method in Objective-C and is usually used as a constructor. This is really an interesting block, so I'll split the block itself into several pieces. That's simple. It's just code that allocates the drop-in controller, not much to it. This is like Java's new. However, you will notice that the brackets aren't closed because the init method or the constructor should be invoked. The init method here is special. It accepts the token as an argument, as well as the request. Notice two interesting things. The client token is just passed, but request is written twice. In Objective-C, arguments are named. That means that you need to type the name of every argument to a method, and you can have two methods with the same name but different argument names. To make matters more confusing, the first argument is a special case that doesn't need a name, so we have one argument followed by the other arguments, each containing the name of the argument, and then the value. So the request argument name and value make sense, but the last argument might seem odd. Handler is an argument that accepts a lambda expression with a callback. That callback accepts several argument types and will be invoked asynchronously when a purchase produces a result. The lambda expression itself checks if the arguments represent an error, cancellation, or success. This code should be pretty familiar to Java programmers. The one weird thing is that Objective-C strings start with the @ character, which I won't go into here. The final piece of code is the presentView controller, which shows the UI. Notice it happens before the lambda expression is invoked, as that is a callback. Also notice we use the Objective-C keyword self, which is the Objective-C equivalent of Java's this keyword. In this particular case, self is assumed to be a view controller. So now that we reviewed everything in the method, it's pretty clear that the big thing that's needed from the Java side of the API is the token and not much else. This is something we can represent with this simple method. Once we implement that in the Java side, we can use generate native stubs to generate stub code for the various native platforms and fill up that stub code. One important piece that's missing from the native interface is the callback code. We need to monitor callback events so we can know if a purchase succeeded or failed. A more common approach would be to pass the callback object instance to the call, but here I use static callback code. The reason for that is simple. Native interfaces have a lot of restrictions on them, and one of those is that we can't pass arbitrary object types. The reason for those restrictions is simplicity and portability. How would you represent an object instance in the Objective-C mapping? To implement callbacks, we use static methods and some platform-specific code. Calling the native interface directly is often a bad practice. Native interfaces are often fragile and should be wrapped in an abstraction that hides potential platform issues. For instance, if the iOS and Android native interfaces have different features, we might be able to hide or abstract it in the Java side, which is normally much easier to do than implementing native code. In this code, we even have an attempt at fallback code based on the JavaScript port of Braintree. It doesn't work all that well, but that's mostly because I didn't pay that much attention to it. This class is mostly trivial since the native interface is trivial too. Notice the code at the bottom that invokes the static callbacks. This is a special case for iOS, where the VM strips away unused code. By writing this, the compiler can't tell that the code will never be invoked, and will keep it in place. Notice that even making a seemingly small change like making flag into a private variable might break this.